Hello.
Hello. Can you hear
Hi.
me?
How are you
Hello.
today? Good.
I'm good, thank you. How are you?
I'm good. Thank
I'm
you.
good.
Good.
Um,
What shall we talk today? Our
Today, can we do not time dilation, sorry, length contraction?
length contraction. Yeah, that's
Yep.
opposite. Yeah, that's another issue. Yes. Okay.
Yes.
Let's go to the time dilation. So I just write down the formula for time dilation first. Okay. So the
Okay.
time dilation is just time dilation. So the formula is so we just use proper time. The time will equal to gamma times the T null. T null is proper time. If you want to write a complete formula, that would be this one. Okay.
Mm-hmm.
Did you at the school? Did you learn the formula for length contraction?
Length contraction? Yes. I
Yeah.
was, yeah.
Yeah. You can write down. We can just put. We just show why it's so. Okay.
Mm-hmm.
Length contraction. So they have used the Properness, right? Do you remember? They have used the Properness. Did their teacher tell you Properness?
Proper length, yeah. So that's the length of the moving object in relation to the one someone in that reference frame, right?
Well, basically the Properness, like a definition of proper time, is such that it actually stay with the observer. Okay.
The observer. Okay.
This is a little bit tricky because you will see that we will encounter same claims when we describe the time dilation. Do you remember? So the basic, I just write down formula here. This would be the formula. Can you see? It's symmetrical. Can you see? But it's different.
Yeah.
So compare with the proper time, the time getting longer, right?
Yeah.
Compare with this, yeah.
Yeah. So
getting longer, yeah. Because gamma
relativistic time.
Yeah. So
it's getting longer.
Yeah, because gamma is larger than. So we know that the gamma is larger than 1, right? Gamma is larger than 1. But in this case, you will see that in this case, therefore, we have the opposite issue because you divide by something, and you will get that the length is always getting short compared with L null. So that will give that L is shorter than L null. Do you agree?
Right. Yeah.
In this case, what we claim that the time is getting longer. So time gets longer with the proper time. So that is two consequences of the direct consequences of the Lorentz transformation. Okay. Okay. Now in school, did you? We know that this formula can be proved from the Lorentz transformation last time. Do you remember how do we write this formula or obtain this formula? Do you remember?
Obtain this? No, I don't remember.
No, okay, and I have to go back. So basically, we got. Can we just put all relevant equation here, right? So we're actually dealing with two frames. One is fixed, another is moving at a constant velocity, right? Relative to the fixed frame. So in this case, you have the observer here, and another observer is actually moving with another frame. It's called the frame S. It's called the frame S prime or S dash. So this is constant. This velocity V is constant, but this velocity is measured by this guy, by this guy. Okay, so that velocity this is so this is velocity. This is x. We just consider one-dimensional motion. This is one-dimensional motion. This be the x, right? Okay. Now, from Galileo, we just start from Galileo. In Galileo's times, and the people argue that the position of for example, the position of this guy the position of this guy is different. Okay, so basically this x is x prime. So there's a simple relation. X will equal to the velocity times t. Okay, this is a Galileo's transformation. That obviously x, this one will equal to the v prime, not v position. It's because we have that is x prime plus vt. You agree?
Yeah.
Okay. Now from here, that's Galileo's. This is Galileo transformation. It's Galileo. So from here, we obtained that. We just rewrite that one. We solve that x prime, which will equal to x minus vt. Okay. We just come from beginning. Today we just start from the beginning.
Right.
Another thing is that we have assumed the time in both frames are absolute. So therefore, there's no change in the time. Okay.
Yeah.
So this is called the Galileo. So this transformation is called the Galileo transformation. Now we know this would be wrong if we consider the speed of light. Okay, if we get so that is true. That's when at lower speed. So when the speed is very close to the c, we have Lorentzius transformation. Do you remember Lorentzius transformation? You just have to time I just write down everything. Yeah, that would be the same. At lower speed, that would be the same to Galileo. However, I just put the time here. Everything you have to be modified. You have to put a gamma here. Do you remember? So that is
that's how you find the
That's right.
Yeah. Okay.
That's Vx times c squared. So this is called Lorentzius. The second one is called Lorentzius transformation. Okay, so the second one is called Lorentzius. Okay, so that is where actually we argue that if you just continue make this argument, we just consider the same one. So if x equal to 0, okay, and we will have t prime will equal to gamma t. Can you see?
Do
you agree? So of course you can argue that if you use a different notation, that will give you some different. This is if you can also argue that if x prime equal to 0, you will get something different. T will equal to gamma t. Okay, so from these two claims, they are just they are making the same statements from different perspective, right? To avoid to get something really new. So Einstein used a proper time, the proper time. Do you remember?
Proper time. Yeah.
The proper time is such that the time is measured with the the observer is not moving.
Yeah.
So therefore, in that way, we will pick up this. Then eventually, we got this formula here. We got this formula. So it's time dimension. I think that's enough. So therefore, that will give you the formula like this. So t will equal to gamma times t0.
Yeah.
Okay. So when you talk about time dimension, then you have to refer a proper time. Otherwise, the claim made by two people are opposite, are contradiction. Because they will say his time is slower, and he will say his time is slower.
Right.
Okay. That is a little bit challenging for the students at this stage, because without making a proper time, then you can't talk about time dimension in the so kind of absolute way.
Yeah. Okay.
Now, similarly, this move to the length contraction, and also you will notice that we have, by analogy, we have used a proper concept. It's called the properness. Properness.
Proper length. Okay.
Yeah. we just use this problem is called air null here. And then we can make this absolute claim. So basically this is somewhere the student get confused, okay? Because if you know use your Lorentz transformation, we can just use Lorentz transformation, one of them, see? If you let t equal to 0, equal to 0, so from, can you just, I don't have it right, I just draw your attention. If you use this equation, can you see this is Lorentz transformation, right? If you make this, if you let t equal to 0, or means his clock equal to 0, and that particular point, you can claim that an x prime is longer than x. So this formula, can you see this one? This is similar to this dilatation formula. This is very one because the gamma is larger than 0. Okay, so given x, you have time after times a factor which is larger than a unit, then obviously this side must be larger, right?
Yeah.
So what does that mean? That the length contraction is also relative phenomenon.
Right.
Okay. So similarly, you can use another. I can write it down this time. So this Lorentz transformation. So this one, I just pick up this one. So this one, can you see that? I pick it up here. Yeah. I can simply we can construct another relation, which is x equal to gamma x prime, provided I put this positive side here, and then it becomes t prime.
Yeah.
Now, if you so that's because you see relative to, so this guy and this guy, when this guy say you are moving toward the right hand side, right? But for this guy, which is on the bus, you will say you are actually moving backward. You are moving to the rest, to the left. Yeah. So that's why to get this formula, we just need to change the sign of the v. That is different from this one. Can you see?
Yeah.
Now.
Right. That's why you need to change the.
Okay. Yeah. Okay. Now this makes same judgment. Now, if we let t prime equal to 0. So we will get what? We'll get x equal to gamma times x prime, which is contradict to the observation we made when we make a t equal to 0.
That x prime was larger than x.
Yeah. Is that confused?
Yes, it is.
Yeah. Doesn't matter. I will show you. This is something you have to, if you want to go into the detail of relativity, that is where you have to pay attention. So basically, I rewrite this formula here, larger one. So basically, you got transformation, right? So x prime equal to gamma times x minus, right? Minus vt.
Yeah, vt. Yeah.
And the t prime will equal to gamma. And that's the t prime minus vx prime c squared.
C squared. Yeah.
Okay. Now, if we just exchange the v, so basically v became negative v, and then x prime exchange with the x prime with x. Yeah, so we got the symmetrical formula that would be the x. This is x prime plus vt prime. Can you see?
Yeah.
T will equal to gamma t prime plus vx, sorry. This t prime, this x, oh, this is wrong here. There should be no prime here.
Oh yeah,
okay,
just t.
Yeah, just t. Yeah, that's c squared. Okay, just remind you. So we have to, let's just cover it up. So this is a mistake. So there's no prime here. Can you see?
Yeah.
So these are all called Lorentz transformation. Both of them is called Lorentz transformation. Lorentz transformation is true that for in Einstein's relativity. Okay. But it's not. But it also gives an asymptotic value. at lower speed, which will be identical to Galileo transformation. Okay, both are the true. Now, can we label the equation here? Can we just label this equation as, say, can we say this equation 1, this equation 2, this equation 3, and equation 4, okay? Now, to talk about length contraction, now we have to, we don't have to, because we know these basic equations now. So in the first place, we can net t equal to 0 in equation 1, okay?
Yeah, okay.
So what do we have? We've got x prime equal to gamma x, okay?
Yeah.
Alternatively, we can net t prime equal to 0 in equation 3. What do we get? What do we have?
Let t prime equals 0 in 3.
Yes.
Then you have x is equal to
gamma, yeah, x prime.
Gamma x prime, yeah.
Can you say contradiction?
Yeah, direct contradiction.
Yeah, that is exactly happened to when we talk about time dilation. If you return to the previous page, can you see? When we talk about time dilation here, if we just net x equal to 0, we got t prime equal to gamma times t. But if we net x prime equal to 0, meaning the clock is located at origin, okay? When we net it to 0, the clock is just located at this particular region, position.
At the middle, yeah.
We got a contradiction, can you see? In either case, we got a contradiction. You agree? They are contradictory to each other. So, but it's not, because this is a logical outcome of relativity. So if you study this, so these two are simply contradicting to each other. Can you see?
Yeah.
And similarly, if you go to this one, can you see they also contradict? Can you see?
But the ones before,
they
weren't contradiction, were they?
No, because why? These are, you see, they give a different relation.
Oh yeah, these ones are, but the time ones.
Yeah, both the time one is also contradiction. Can you see? Oh, hang on. I have rewrite this. This is wrong. So x prime equal to 0. Let me see. X prime equal to 0. This hang on. Let me check. X equal to 0. X equal to 0. Let me see. X equal to 0. You got the first equation. Oh, this is right. This is wrong. Okay. I'll be very careful.
Okay.
So this time I have to have that would be different.
Yeah, I see.
Correct. Yeah. Okay. Calculate prime. Can you see contradiction here?
Yes.
So that is why, that's why if you have time, you really have to looking for what is a proper time, okay?
Proper time, yeah.
And
so you have to do the same there.
That's right. You have to also make assumptions. There is a proper length that the time, how to say, the both time dilation and length contraction is absolute. Is absolute.
Okay.
So you have to, that is a trouble with this Einstein's this phenomena. But unfortunately, this discrepancy or contradiction was not mentioned in many textbooks.
Oh, why wasn't it mentioned?
Yeah, can you follow me?
Yeah, I can follow.
So in many textbooks, we just use this formula, okay? We just use this formula.
Yeah.
We just say, well, if the move and the time measured will be getting longer. So what does it mean that? So they are talking about the same, they are measuring the time. For example, they are measuring the interval of two events. They are measuring two events. Now, for these people, for this observer who's traveling with this frame, they say that the time is t0, okay?
Yeah.
You see? So when that equal to t0, but for this guy, they will conclude differently.
Yeah.
And they will say the time happening is not that time. So this is a guy, what is so therefore, the velocity here, more important, this velocity, I use this, so this velocity is the velocity that the frame prime is actually travel at constant velocity.
Right. Whatever frame that.
What frame is that?
Yeah.
But for this guy, he believes that the time, it should be longer than the measured by he would claim that the time were getting slower because according to his clock, I should draw a clock here. In either frame, you have to draw the clock.
Mm-hmm.
Yep. So for example, he got a clock, and also he got a clock. Okay.
Right. Okay.
Okay. So basically, the time for this guy, for this moving on the moving frame, will be T0.
T0. Yeah.
Yeah.
Because it's from the perspective of the
from
first.
perspective. Yeah, that's how we write this question here. So
yeah,
therefore, but this guy on the fixed frame will argue that no, your clock, the time interval according to my measurement would be longer than yours reading.
Longer. So they look like, to them, it looks like the people who are moving have less time.
Well,
that time is taking slowly.
For example, I just put probably the cartoon like that to explain to you what's the time dimension. So with this guy, they say I just write it down. So if this guy say my time delta t, okay, is 1 second, okay, exactly,
Yeah.
okay. But what he would say, he said no, his first reading, he said no, my time interval is actually 1.2 seconds. Can you see that?
Yeah. Okay.
So they are counting the same thing. Okay.
Yeah. Okay.
So therefore, you can see from, let's go to next page. So in this case, we have to introduce a proper length, right? The proper length. Otherwise, their claim will be contradictive to each other.
Okay.
Can you see that?
Yeah.
So in this case, we just go to the same frame. If you want to draw this frame, same frame here. So what we can say that is a frame. That is a frame is moving relative to the fixed frame. So in this case, so there'll be our S, it'll be S prime, and which is moving at velocity v. This is X prime, this is X. Okay. Now according to here, so you just put the length, there's this object. So for example, there is object, probably is a metal bar, right? Whose length is zero. But this is according to this guy on the frame, see? So the length is 0. But for this guy, and he said no, your length I measured is L, okay?
Yeah.
Okay, and L is, in this case, L is shorter than yours. Is shorter than yours. That's how the contradiction happened. Can you see?
Right. Because
why?
Yeah,
because in this case, the properness will be the length which move together with this guy. You see?
Yeah.
So therefore, we can, from this formula, we can see that that we return to the equation of the length contraction. L will equal to L naught divided by gamma.
L is equal to L naught divided by gamma.
Yeah. So that's
using the first one.
Yeah, that's the first one. It's the first argument.
Right, okay.
It's first argument. Okay.
Right, okay.
So that makes sense. In other words, X will equal to X prime divided by gamma.
Gamma, yeah.
Okay.
And that's how they got that.
That's how it goes that as function. So I think in high school, people will just use this formula and just calculate the gamma, where gamma is just do you remember the gamma? Gamma factors being always used. Yeah, that will say that, for example, they will give proper ratios and they will work out, you can calculate R. They just use some calculator to work out some numbers. Say, for example, sometimes we depending on the ratio of the velocity over c. Okay. I hope this talk will give you the some detailed explanation of these two well-known phenomena. One is time dilation, and another is length contraction.
Length contraction.
Okay.
Yeah.
Now, if you still do you still find difficult to understand?
Well, in class when we were talking about this, one thing I found confusing was thinking about length contraction when there are two. Yeah. So like the scenario we used was a rocket.
A rocket,
traveling from a rocket traveling from Earth to some other star.
Yeah, it could be a rocket, could be the bus, doesn't matter. It could be the bus, could be. I still prefer use this simple description. This could be the bus or could be the rocket. Okay, so the whole thing could be the rocket. So just draw the cartoon word. So the whole thing here could be part of a rocket. You see, so which is traveling at the proper velocity v. Yeah.
Yeah.
Because these are two observers. One is observer in a rocket, another is observer not moving on the Earth. That's the same thing. So this x prime is x. So what is your description? What you?
So from my understanding, I think the stationary observer will well, assuming like the rocket is traveling very close, like close to the speed of light, the person on the stationary observer will observe the length of the rocket as what do you call it? Contracting, right? It'll appear short. It'll physically appear shorter.
No,
than it is.
No, it's not. Everything comes around with their clock. You see, if your teacher tell you everything is originated from the clocks they use.
Okay.
Because in the essence in relativity is that you have to use a local time. You have used your own time, a clock. You cannot share the common or absolute time. So basically, you can consider that the time dilation, the length contraction is logically consequences of you use the time dilation. I will write down this for you. Can you see? So if you have time dilation, you have time dilation. We know what is the reason now. Time dilation. Okay. That will make logically come to the length contraction. I show you why. Contraction. Contraction. Because we can consider that there's an object. See this object with length, proper length here. Of course, it also move. So as air no, it's move relative to this guy. This is S prime. This is S. Sorry, other way around. This S. This is S prime. Okay. So how can this guy move this length when this object is coming? So they can reset their rule. Previously, this object here, can you see? At the beginning, is it here? So when the object just arrived here, he count his time. Can you see? So the object is moving, remember?
Yeah.
So he count his time, and his time will give you the proper rate, for example, the proper rate, okay? This time will be, can we call it T, just call it T? Yeah, because at the beginning, we just starting to count. We started to count. This object can move, right? Now, when we started, so that will be the case when I just draw this different color. So when did I count the T? They were when the object just passing, the end of object just past the origin.
Yeah.
So that's the count, the stop the counting time, right?
Okay.
But unfortunately, in this case, he has used his local time.
Right, okay.
So therefore, because that is the velocity, what you have to count in is that you have to, in this case, the length of the proper length, or with length made by this guy, divide by his time, okay, by his time. Okay?
Yeah, okay.
Because you see, they have to use this air travel. This is air. This is bar. This is bar travel. You see, which is moving together with this object, right? So
right, okay.
that, of course, this ratio will give the relative velocity. Can you see?
Yeah.
That would be this y. So this is a velocity, constant velocity, relative to the frame, for the frame S, right?
Yeah.
On the other hand, now this from point of view, that's this observer. This observer in the S frame, what he did, okay? Now, on the other hand, the observer on the S prime frame, they can do the same measurement. Now, this time, the object on this frame will be called L. You agree?
Yeah.
Okay. Now, this L, then he will make the same judgment. However, he will going to use the same method to measure this length. Okay, but he has used his time.
Right. T naught.
T prime. Can you see that?
Oh, T prime. Yeah. Okay.
So that's explanation. So that's why this is a logical consequence. That's this in mathematics. When you see this sign, it's just logical consequence. Logically. So basically, from this fact, we can write it as L naught will equal to T over T1 over T, not T1, just T, will equal to L over T prime.
Yeah.
Okay, if you do some multiplication, you just simplify that. Therefore, L naught divided by L will equal to T divided T prime. Can you see?
Yeah.
So I hope this equation will give you the explanation. So because T1, because T equal to gamma T prime, right? Oh, can you follow me? Wait a second, okay.
L naught is equal to T prime.
Yeah. Can we say that equal to gamma?
Yeah, okay, yeah, that makes sense.
That makes sense. Because why? You understand now. Because T equal to gamma times T prime. Okay.
Yeah, yeah.
So therefore, logically, what we can say. So therefore, we can prove from this formula, just from this formula, what is L? L have to equal to L naught divided by gamma. So that is a proof of the length contraction are the direct or logical consequences of the time dilation.
Right, okay.
So this time dilation, and this is a length contraction.
Right, okay. Can you give me a second? I just want to take some notes.
Okay.
T is equal to... can we use T prime, not T prime, T naught as well?
Oh, you can use T naught. Yeah, you can use T naught. And here is you can T naught. So this is in this case, T prime is a proper time. So this one I can write down here. So in this case, T prime or this clock, the reading of this clock. So reading of this clock, I just use more precise distance. The reading over here, this reading T prime will be considered as a proper time. Okay, not the T0, T proper time. So can I just draw some cartoon like so this clock is slower. Can you see the clock is slower?
Yeah. So
so time connection were the length contraction is just logical consequences of time dilation.
Yeah.
Because the observer must use their local time to measure the length on the other frame. Right. It's called observation. Perhaps I will just do another cartoon for you. So this one. So in this case, Can we consider this the length? This is the length. Can you see this is the length of the object on this moving side? So when the moving, we started to count. Can see, and with the count, time is 0. Okay, and then the t1 is moving. The car is moving. At the end of this object, we just stop. So the time taken will be exactly equal to t. Do you agree? According to this observer will be t. Okay. Now that is how from this observer by this observer we can get this relation. Because this bar also move at the same speed, right? This bar will move at the same speed together with the frame. This is velocity. So that is why this formula is true. Can you see?
Yeah, for that observer in that reference frame, right?
Yeah. So if you want to take a note, take a note, you just say that the two observers must use their own clock.
Okay.
Okay. And but these two clocks, according to time dilation, one is slower than others. I read a summary for you, if you wish. The two observers, the observer.
One must be slower than the other.
Yeah, observer must use his own clock. Okay?
Yeah.
Okay. Number 2, the observer must measure the length of the object, of a moving object, on the other frame. Do you agree?
Yeah.
Because you see, relativity is about you look at the same phenomena from different perspective.
Yeah.
Okay. So hopefully you can understand why there's why we say the length contraction is a logical consequence of time dilation.
Yeah, that makes a lot more sense.
That makes sense. That's right. Yeah. Because they have to use his own clock. Okay, I just use a different color. I don't want to make it too crowded here. So because they have to use his own clock, that implies that this observer will use the t prime and this proper time, while this guy have to use the t, right?
Yeah.
And on the other hand, they cannot just measure the object on its own. They will just make a judgment. Of course, both men will claim that they are using the same object. Now, that is something I disagree with you. You say that physically there's change. There is no physical change. No physical change. I must emphasize that the length will be the same. You can see they can buy same object. Okay, they can buy the bar, we can buy the boxes, we can buy, any object. Do you understand? Yeah. But unfortunately, in relativity, we even have trouble. When the time became relative, the measurement also become relative. Okay.
Measurement also become.
Yeah.
Okay. Yeah.
Physically, they are the same. I should make it exactly the same. Okay. Yeah. Physically, they are exactly the same. However, depending on which observer, they will make a different claim. So the guy, one will say, oh, this length is L. Another will say it's L0. Where are we now?
Hello?
Are you here?
Yeah.
I think that's the explanation that everything is relative, right? Both time and length, this basic unit have to be the reading, not the absolute, that is the physical length, but the number of reading will be changed, That is the consequence of the relativity, all right? Perhaps I will use some time to tell you another simple way to obtain the time dilation. So if you just consider the same diagram we often use here. Now, if you consider this scenario, so this time I will consider the guy on the moving frame is doing experiment. Okay, he's doing experiment. So what he did, so he just used a flashlight here. Okay, there's a mirror here. So this could be mirror, but the length is given, you see. So this distance is given. So basically use a light source here that we just slow down the traveling of light. So this is light traveling from this vertically, by this guy. And of course, he's used his local time. He measured with his clock. His clock, the reading of his clock is T prime. Okay, is X prime, this is X. So because we assume that the speed of light is constant everywhere. Do you agree?
Yeah.
Therefore, the distance they travel that far can be written as, so this distance, this side, can be written as C times T prime. Can you see that?
Yeah.
Now, on the other hand, this is a displacement. The frame has moved. That will equal to V times T. Now, this is this observation is made by this guy, which is on the fixed frame. This is called the fixed frame. Okay.
Yeah. Okay.
So I just use some simple method to prove without using Lorentz transformation, because where they have used, you have defined what is the proper time. Okay. Now, what would happen? So this is light source here. So the original, the light source is here. So the light source is moving. Do you agree?
Yeah.
But for this guy, they would say, of course, he will use his own time or use his own clock. Can we call this C? So this is, he can use his clock, which is called T. Now, I don't want to make it too crowded here. So basically, he uses his own clock, or somewhere here, he's using his clock. The reading will be T for this event, okay? So the event is that the light to travel. So light to travel from this one upward vertically on the moving frame. But for this observer, he would say differently. He will say the light to travel from here to here.
Right.
You agree?
Yeah.
Can you see that? If someone just threw a ball upward, and for the observer on the ground, we thought that the ball will travel not along different direction.
Yeah.
Okay? Now that would be just remind you, this is a right angle triangle. Now my question is, what would be this distance? A hypotenuse, what is the longest side? How about this distance? If the observer uses his own time, use his own
longer
clock.
than,
No, you have to slow down a little bit. You have to slow it down here. This is axiom in activity. This is a basic assumption. Okay.
Okay.
So which implies that the constant is constant everywhere.
Right. Yeah.
So including these two observers. And when this observer uses T here, can we just emphasize the importance of the C? And this guy must also assume this is C2.
Right, yeah.
That is consequences, this consequence of this axiom, you agree?
Right, yeah.
So remember, that is a starting point of Einstein's relativity. Okay. Now, perhaps you can help me now. how do we find the relation between t, the time used by this guy, and the t prime used by this guy? Can we find the based on this right angle triangle from this right angle triangle?
So using Pythagoras, maybe we can get
use what?
dt Pythagoras.
Yeah, that's what Pythagoras theorem. Yes, can you write something from your side?
Let me see.
Can you write?
Yeah.
Oh, good.
Okay, I'll try. Writing with mouse. Be a bit bad. Okay, so v t squared.
Good.
Plus c t prime.
Yes.
Squared is equal to.
Okay.
T.
Yep, that's it.
Yeah.
Can you continue? Can you solve the relation between t and t prime? So we need to find the relation between t and t prime. So t and t prime.
So isolate t prime.
Okay, it's up to you. It's algebra. It's a high school algebra now.
Equal to okay. Now,
yeah.
T. Oh wait, no. What was I gonna do? Oh yeah. V t squared. T squared is equal to.
Oh, be careful. Oh yes, that's right. That's right. That's right. Yeah. Yeah, that's right.
Okay. And then from there, oh, you want to get it in terms of one thing.
You have to be careful. These are two different t. One is t and t prime are different, and they are not. They are just a reading by the two observers. Yeah.
Yeah. Get rid of that.
I give you a hint. You have to separate. You have to separate these two. You have put one t on the one side, another t on the other side of the equation.
Yeah. Like this then. And then make it t squared or t prime squared is equal to. Oh, you want to get rid of the v as well, don't you? Because that's a.
Well, almost getting there. You're almost getting there. Yeah. I'm sure you can got the formula for time dilation.
The formula for time dilation. You could take the. Make this t squared. T squared minus.
Yeah, have you got
t squared?
Yeah.
Over c squared.
Yes.
Oh, wait, no,
wait. Nearly.
No,
this is correct.
Yeah,
that's correct. Yeah.
So
this is all right. So this part, yeah, go on. I just waiting for you. Yeah, you should be able to work it out.
Then t prime is equal to, take the square root t out. 1 minus v squared. V squared.
Good.
Yeah. And then that'll be?
Yeah.
Go to t.
Mm-hmm.
That's just gamma.
Yeah,
right?
it's gamma. Yes,
1 over
right.
gamma.
Yeah.
Is it divided by?
Oh, you have. I just write down what is gamma. Gamma is 1 over square root.
1 over. Yeah.
1 over.
So this is divided by gamma then, right?
So gamma equal to 1 divided
1
by
over.
1 v squared c squared. Okay, that's gamma. Yeah.
Mm-hmm.
Go on.
So
okay. One more step.
Like
final step. One more step.
Final step t is equal to.
That's right.
That?
That's right.
Yeah.
Or in other words, t will equal to t prime, which is proper time in this case. Can you see? Because we see because this is not moving, so this is time. That in this way, we can also obtain the formula for the time dilation.
Yeah.
Okay. Now, if you combine this formula, this method with the one I just showed you today, this one, then you can derive the formula for non-state contraction as well. Can you see?
Okay.
Because time dilation will imply this our time dilation formula. Okay. Although we obtained it from Lorentz transformation 2 weeks ago. Right? But this time, this is another method, and you can actually direct the formula for time dilation. Okay.
Right. Okay.
So relativity is not as that complicated.
Complicated, right? It's just those two concepts.
So in this formula, which t is longer? Give me a try. Which t is longer?
Which t is longer?
Yeah.
This will be.
Can you use the inequality sign?
T.
Equality.
Yeah. I'll use this color. T is, I think, greater like that.
Yeah. Which is longer? Because gamma is not gamma is larger than 1. You see.
Oh, it's larger than 1. Oh.
Okay. Yes.
Yeah. It's not smaller. Right.
The reason is larger than 1 because these always take away from. Yeah, that's right. So can you see? So time is longer. So how to interpret this one? So time is longer. Do you agree? So time appears longer. Now, I hope you will understand this. Can you describe me? Can you tell me how did we obtain this formula today on this page?
In this formula, on that page. Okay.
Yeah.
So in this diagram here, you can see in the moving reference frame, there is a light that's being beamed up.
Yeah.
That's being beamed up. And from the perspective, like from the S prime reference frame.
No, sorry. So this is just S. I have to remind you, I make another mistake here. So this is S. So this guy is S. This is S prime. This is S prime. Yes, the other way around. Yeah. Go on.
Yeah. So on the S prime one, it looks to the observer on the S prime as if it's moving up.
Yeah.
And the speed is c.
Yeah.
So that distance can be considered ct.
T prime. Yep.
Yeah. Ct prime. But to the observer in S, the reference frame S.
Yeah.
The distance that the light traveled looks as if it's traveling in a
incline.
Inclined.
Diagonal. So that is also actually that's a light beam, right? It's also the light flash.
That's also the light beam. Yeah. And since the speed of light c is constant, so that the distance of that is c times t normal.
Yeah.
Right.
Now the time they have used its own time. You see, whenever you discuss relativity, perhaps next time we can solve some real problem, right? So you have to first one you have to choose the observer, and then immediately you have accept. He uses his own time. He uses his own clock. Okay, go on. Okay, go on.
And the distance between the two reference frames is given by VT.
Yep.
So
according to the observer in S frame, right?
Oh yeah. According to the observer in S frame, the distance is given by VT, or otherwise it would be minus VT, right?
Yep, that's right.
Yeah. Okay. Right. Then using the Pythagorean
theory,
identity,
yeah,
theorem, you can derive the formula for time dilation.
Yes. Yeah. I think this is simpler than the one we use, is the Lorentz transformation.
This very easy to understand. Yeah.
But this is easy to understand. But as we will move forward, if you still wish to learn more, and this is more essential. So Lorentz transformation is essential. There Lorentz transformation, of course, we have to, although we have to using what we call the proper time, right? Is that? Where is it? Yeah, this one. Oh, doesn't work. This one. Oh, this one. So Lorentz transformation is also don't forget Lorentz transformation is essential. Okay. Although when we have used the proper time, you know, a little bit tedious, right? You have used the proper time, but they can give us more informations. If you one question remain unanswered is that the relative speed. Okay. Yeah, perhaps next time I will discuss how the formula for the relative space. Well, I give you time. I give you the time to think. Now, give you this is your homework to think how to obtain the. I just change it to the color.
How to obtain?
How obtain the relative speed? Okay.
Obtain the relative speed. Okay.
Okay. So basically, we have this formula now. Can we just go to Galileo first? This Galileo's transformation is simple, right? That is x prime will equal to x, right? Plus minus or minus. This is minus vt.
Minus v.
Okay.
Yeah.
Now, in Galileo's time, because t prime and t are identical, right? So therefore, if you just consider if the object is moving at the velocity u, right? Now, if this object is moving, for the reference, so they have two results. One is we know this object is moving, but for different observer, their velocity will be different. Okay. Now, in Galileo's time, that the velocity u will equal to delta x, delta t, right?
Yeah.
Yeah. And the velocity observed by another observer will be simply delta x prime, but delta t. Can you see that?
Yeah, because time was assumed to be constant, right?
Okay.
Yeah.
Absolute. Okay. So based on this idea, what we can say, if you just delta them, say, can we just delta? So delta x prime will equal to delta x minus v delta t, right? So if we divide the delta t on both sides, so we divide by delta t on both sides, what we will get? Delta t. Have you started average velocity formula?
Average? Don't think I remember.
If the object is moving, okay. Now at a given time, for example, from here to here, the displacement is delta x, and time taken is delta t. So the velocity will equal to the ratio. That is the velocity.
The velocity will equal to the ratio.
Do you remember what is the velocity is? That's called the velocity.
Right. Okay.
you forgot what is the velocity?
Oh no, that's a rate of change of displacement. Right?
Okay, that's right. That is velocity. Yeah. Okay. Now, so consequently, we can argue that the velocity prime will equal to velocity minus v. You see, that is Galileo's
minus v. Yeah.
Do you agree? That is a Galileo's transformation of velocity.
Okay.
So in other words, so you can rewrite this formula in slightly different form. For example, you can rewrite as u will equal to u prime plus v, you see?
Yeah.
So both are equivalent. These are called Galileo's transformation, okay? Because in Galileo's transformation, number one, t are absolute, okay? Number two, there's no gamma factor. Now, if you're interested to want to try out before next lesson, then that is something I give you a hint.
Okay, so try to find.
Yeah. Now in relativity, that is in Galileo's transformation. Okay. Now in relativity, the velocity must be defined differently. That be delta x, delta t. Can you see?
Yeah.
But the t prime, be careful, must be defined as a delta x, delta t prime. Can you see?
Delta x, delta t prime. Yeah.
Okay, that's different. So this is Lorentz. In that way, you have used Lorentzian transformation. Okay.
Does the x in the u dash, does the x have to be a dash as well?
Oh yes, you are right. Thank you. Okay. You are right. Yeah. That is essential. Can you see? This is essential. Can you see? In this case, we just use. Can you see? This is equal to v. That equal to v dash in Galileo's transformation. Okay. But be careful. This is different. Can you see? I draw these two circles here. Okay. Now, if you wish to try, then you can use Lorentzian transformation. I give you result. If you can solve that problem. That's x prime will equal to u. I think is 1 plus v squared, c squared, something like that. I'm not sure. You have to check that. That is
something similar to that.
Yeah, so something similar to this one. Okay, something similar to this one. Probably this factor is not correct. This factor could be vx, could be vx. Just remind me. So this, I will double check the formula before you get lost. Yeah, so nearly correct. So that t prime will equal to u minus v, and this will be t prime will be minus c. That is, oh sorry, that's u minus v. Can you see? U and v are different, divided by c squared. So that is correct formula. If you want to try, you just try to if you can prove this formula. That is a formula in relativity. Hello? Get lost? Okay, we'll stop here.